All right. For the next problem, we've got a beam. A beam is just like a log. Wooden beam of mass 1.1 kilograms, suspended from two cables. Beam is 1.8 meters long. And the cables are anchored at each end. One is angled at 67 degrees above the horizontal. A mass of 1.8 kilograms is hanging from the beam 0.5 meters away from that. So 0.5 meters away, we've got a mass. And then we want to find the tension in both cables. So here we have cable 2 at some unknown angle. Meanwhile, the wooden beam presumably has uniform mass, so that would its gravitational force would act halfway down the length of the beam, which is 0.9 meters. So, alright, we've got M1 here, and this is mass of the beam times G. So we want to calculate a way. Now, where's a good place to set your pivot point? I would choose here, because we have two unknowns there, the y component and the x component. Again, you can do whatever you want. So from the masses, they would tend to cause the beam to rotate clockwise. So for writing that torque equals 0, we've got minus mass of the beam times G times distance from the pivot point, which is half the length of the beam, 0.9, minus this other mass, which is 1.8 kilograms, G times its distance from the pivot point. This is 0.5, so this distance is 1.8 minus 0.5, which is 1.3 meters. And then this tension would cause the beam to rotate this way, clockwise. So we've got plus T1 times the distance is the full length of the beam. Actually, I'm going to run out of space here, so I'll put this on the next line. Plus T1 times 1.8, and this is acting at an angle of 67 degrees from the beam. So we can calculate what that tension is right away. Move these over to the other side, they become positive. And then divide out 1.8 sine 67. And we get that that tension is about 19.7 newtons, which I will store as P for tension. Okay, and we can start writing equations. Writing our force equations in the x direction. We have only two forces. We've got T2 cosine theta. Actually, that's not smart. I'll call that T2x, the x component of that tension to the left. And then we have the horizontal component of this tension to the right. Plugging in our stored value times cosine 67. When we isolate T2x, the negative, we move this over, which becomes negative, the negatives cancel out. So we get the x component of that, 7.695. And in the y direction, we have T2, the y component of T2 upward. We have the y component of T1 upward. And we have the gravitational force of both the beam and the other mass going downward. All that adds up to 0. So using our stored value and these values, move this over, the gravitational force becomes positive. And then we subtract off T1 sine 67, and we get this equal to 10.29 newtons. Store that as y, and do our usual thing to calculate magnitude and direction. Oops. All right. Finally, we have one last problem to do. Oh, I found my mistake here. I made a sign error. If you're looking at the packet, so the acceleration of this block will be downward, right? So that downward acceleration should have the same sign as the downward gravitational force on the block, and the opposite sign as the upward tension force on the block. So what I did, I plugged in this acceleration as positive, but then I had a positive tension and a negative gravitational force when they should have been flipped like this. So then if you do that and then go through what I was trying to do before, you would see that you get the same answer for acceleration as you did originally. Finally, last problem. Got the boom of a crane. Is uniform, 3 meters long, weight 500 newtons, supports a tree stump, and associated earth, so I guess there's dirt clinging to the tree roots or something, with a weight of 800 newtons at its far end. The boom makes an angle of 53.1 degrees to the horizontal, and the tie rope makes an angle of 36.9 degrees to the horizontal. Notice these add up to 90, so that means the angle between this rope and the boom is 90 degrees. So we want to calculate the tension in the tie rope and the force acting along the hinge in the horizontal and vertical directions. Well, so let us consider first, as usual, the net torque. Now we don't know the horizontal or vertical components of the force acting along the hinge, so as usual, I will make that my pivot point. So then what forces do we have acting? Well, we have the gravitational force on the boom, and we've got the gravitational force acting on the tree and tree trunk and stuff. And we have the tension in this tie rope. And then some unknown force of the hinge that could have an X and Y component in general. So, torque, this would cause the boom to rotate counterclockwise, so minus mass of the boom times G, which is the weight of the boom, which is 500 newtons, we know already. That acts halfway along the length of the boom, so it's 3 meters long, it's 1.5 meters away. And then what's the angle here between these two? Well, we consider this is 36.9, which means that this angle right here is 53.1, which means that this is 36.9 again. So that's sine 36.9 degrees. And then the same thing for the tree trunk. Its weight is 800. It's 3 meters away though, but then that force makes the same angle to the boom. And then the tension in this rope would cause the boom to rotate counterclockwise. That's plus tension. That acts 3 meters away. And the tie rope, as it turns out, is actually perpendicular to the boom, so that's a sine 90, which is 1. All those add up to 0. So then for part A, we learn that the tension in the tie rope is about, 500 times 1.5 sine 36.9 plus 800, times 3 sine 36.9 divided by 3. Tension of the tie rope is about equal to 630.4 newtons. All right. Then, for part B, we start writing our force equations. In the x direction, we have a force from the hinge, some x component of that. We have the x component of the force from the tie rope, which is going back the other direction. Tie rope makes an angle of 36.9. And that's it. So I'm going to store that value. It's T times cosine 36.9. And we get that the force from the hinge in the x direction is about 504 newtons. In the y direction, we have the y component of the force from the hinge. We have the y component of the force from the tie rope. And then we have the weight of the boom and the weight of the tree trunk. So Let's give you a couple more. V equals 0, so then we calculate that 500 plus 800 is 1300 minus t sine 36.9. We get the y component from of the force from the hinge is about 921.5. It actually just says calculate the force acting along the hinge in the horizontal and vertical direction. So horizontal, vertical, so you don't need to do magnitude and direction.